Welcome to the High Voltage AI Podcast. This is Alex Reed, and I'm thrilled you're joining us today, Wednesday, for another deep dive. This is all part of our special week-long series that you've been seeing in the PXRG newsletter on Substack. This entire series is really engineered specifically for you, our fellow electric utility engineers. We're exploring the intricate world of overhead and underground construction types, getting into why we choose them and understanding their unique characteristics out in the field.
And that's exactly right. I'm Emma Quinn, and it's great to continue this. On Monday, we really dug into heavy angle framing, remember? Then yesterday, Tuesday, we unpacked vertical framing, trying to understand their critical nuances and, well, their applications.
Right. And today it's all about putting that knowledge into immediate action. I mean, imagine you're out there maybe doing storm assessment or perhaps mapping a new circuit for an upgrade, and you walk up to a pole. The critical skill really is being able to read that pole instantly to understand its structural story, at a glance. So our mission today is to give you basically the ultimate field guide for identifying different types of framing built around a powerful, almost like a diagnostic decision tree from our source material.
Yeah, and what's fascinating here is that this isn't just about, naming things. It's a systematic approach. It's designed to prevent costly over-design, which, let's face it, ties up resources and inflates budgets, but equally vital to avoid dangerous under-design. That can lead to structural failures, service interruptions, and frankly, severe safety hazards. So whether you're assessing an existing structure or planning a new one, mastering this quick field identification is just invaluable.
Okay, so let's dive straight in. Let's unpack this. When you're standing there in front of a pole, ready to read it, what's the very first foundational question this diagnostic tree tells us we need to ask ourselves?
Okay, the initial clue, the absolute first question to pose, is about the insulators. What type are holding the conductor? This isn't just a minor detail, it's the bedrock. Because different insulator types, they signal fundamentally different loading conditions. That immediately dictates the framing philosophy.
Right, so we're looking at a critical distinction right off the bat. On one hand, you might have pin or post insulators. When you see these, the conductors are rigidly attached, often on top or maybe directly to the side of a crossarm. The key visual here for an engineer out there is that the conductor looks fixed, almost like it's part of the insulator itself. Pretty straightforward visually.
Precisely. Pin or post insulators are typically for lower voltage distribution, generally. Their presence tells you that the primary load transfer is direct and vertical, mostly just supporting the conductor's weight. The rigidity of that connection means they're usually designed for through-line applications where, significant unbalanced tension isn't the main worry. It's your first indicator of a relatively simple load scenario.
Okay, now contrast that with dead-end or suspension insulators. These look different immediately, don't they? They're often longer, maybe those multi-unit strings of discs or sometimes a substantial ceramic post type. The conductors aren't fixed in the same way at all.
Right. And what's critical here is how the conductors interact with them. With the suspension insulators, the conductors are literally suspended, right? They hang freely, allowing for movement. Dead-end insulators, on the other hand, well, they signal a termination. The conductor actually stops at that point, pulling directly against the structure. In the field, you look for that visible sag of a suspended line, or, maybe more dramatically, the clear termination where the conductor's full tension is concentrated right at the insulator. Often you'll see the line visibly pulling against the pole or a crossarm. This instantly tells you, okay, we're dealing with high tension forces here.
Got it. So once we've identified dead-end or suspension insulators, we know we're dealing with some serious tension. That leads us to the next critical question in our diagnostic tree. Does the conductor terminate at this specific pole, or does it just continue past it?
And that's the key distinction. If that conductor doesn't continue on to the next structure, if it literally stops right there, then you are unequivocally looking at dead-end framing. This isn't just a design choice. It's an absolute necessity structurally. You'll recognize it by its sheer robustness. Often multiple crossarms, heavy-duty steel hardware, and almost always substantial guying. We're talking multiple down guys maybe, or perhaps extensive bracing, visibly countering that immense tension from those terminated conductors.
Okay, so that guying, that's our unmistakable visual cue then, yeah? It's the pole visibly bracing itself against the conductor's full pull. But what happens, though, if you have conductors terminating from both directions? Or maybe you have a dead end on one side and perhaps a simpler pin-post arrangement on the other, creating significant unbalanced pulls.
Okay, good question. That's where you immediately jump to identifying double dead-end framing. If you see a dead end on one side and then any kind of significant load, maybe another dead end, or even a pin post carrying a substantial through line on a corner on the opposite side, well, that structure needs to manage forces from multiple vectors. In the field, you'll spot this by the reinforced appearance, often with cross arms mounted specifically for bidirectional pull and guying strategically placed to counter pulls from potentially opposing or, non-aligned directions. It's basically a pole designed to be a real linchpin in the system.
All right, that makes sense. So we've covered the scenarios where conductors stop, dead end and double dead end. But what about the more common situation where they continue through the structure? Our diagnostic journey kind of shifts here, right? Does the conductor continue, but maybe with a surprising constraint that forces an atypical solution? This leads us to something really clever in utility design: slack span framing.
Yes. This is a fascinating solution. It solves a very specific, very real-world problem. With slack span framing, you'll typically see clear dead-end construction on one side of the pole you're looking at, complete with robust guying. That looks familiar. But then on the other side, the conductors continue to the next structure, but at a noticeably reduced tension. They're often supported by simpler pin or post insulators over there. The visual cue is really unmistakable. That outgoing span of wire will look visibly looser, more sag.
So the pole we're actually standing at is essentially compensating for something happening downstream. It's acting like a tension breakpoint almost.
Precisely. That's exactly it. Its ingenuity lies in its purpose. It's used when you simply cannot install guy wires at that receiving pole the very next pole down the line. Maybe because of intractable site constraints, think poles right in front of public sidewalks or busy driveways, or maybe areas with really rocky terrain where anchoring guys is basically impossible or would create a hazard. So the pole you're looking at, therefore, has to absorb the entire unbalanced load from that dead end side, and then it releases it into a slack span that requires no real tension support at the next structure. And the pole you're observing, it often looks much stronger than you'd expect for just a through pole because it's handling that significant one-sided dead-end load.
That is a truly brilliant workaround.
Wow.
I can think of several times, early in my career where I saw something like that and was just puzzled until someone explained the why behind it. Okay, now let's talk about the most common through construction scenarios, where conductors continue past the structure in a more, let's say, typical way. Here, our decision tree guides us to evaluate angular deviation. How much is the line turning?
Right. And the key question for identifying angular deviation, surprisingly maybe, often boils down to something simple. Is the conductor tied on the side of the insulator, or is it tied on top? A rigid side attachment, rather than a simple top tie, is usually a strong visual indicator of a directional change, even if it looks quite subtle.
And if you see that side tie combined with even a slight bend in the line path, you're probably looking at light angle framing. You'll observe a gentle turn, often less than, say, 30 degrees in the line route. The conductors are visibly pulling a bit to one side, necessitating those specific side ties in the insulators to handle that resultant force.
That's exactly right. Light angle framing provides that modest additional structural integrity needed to manage the resultant forces from minor directional changes. It's sort of an intermediate step in terms of reinforcement, definitely more robust than a perfectly straight run, but certainly less beefy than a heavy angle structure. The gentle curve of the line combined with those specific side attachments are really the key field identifiers. It's a subtle shift, but it tells you a lot about the load on that pole.
Okay, so if we've gone through our checks and haven't seen any of these specific indicators, no dead ends terminating, no significant angles with side ties, no slack, spans, what's our default assumption about the pole's function? What does that basic setup typically look like in the field?
Well, if none of the special conditions we've just discussed apply, then the system, or our decision tree, defaults to tangent framing. This is your workhorse pole, right? It's the most common type of through construction where conductors just pass continuously and relatively straight from one span to the next.
Gotcha. So in these cases, you'll see pretty standard pole strength, probably minimal specialized hardware. And the conductors are typically just tied on top of pin or post insulators, or maybe simply suspended straight through on suspension insulators if it's higher voltage or a longer span. It's the most economical and, the most common configuration. Designed for normal operating conditions with minimal structural loads beyond just basic suspension. This is your definitive straight line pole. No obvious bends in the line, no terminating conductors, and usually no complex guying unless it's just for some minor balancing or maybe specific terrain.
Exactly. So, okay, you're out there, you've used this framework, you've swiftly identified the framing type, tangent, light angle, dead end, whatever it is. But beyond simply putting a name to it, Why does this systematic diagnostic approach truly matter for an engineer or a supervisor in the field? What's the deeper implication here? Why is this skill so important?
Yeah, that raises a really important question. What does this all mean for the big picture of utility operations day to day? Understanding these framing types isn't just some academic exercises. It directly impacts several critical facets, some maybe less obvious than others.
Absolutely. First off, cost optimization. By accurately identifying existing framing, you ensure that any modifications or replacements are perfectly matched to the actual structural requirements, not just guessing. This means no over-design where it's simply not needed, which optimizes material usage and significantly cuts construction costs. It's about designing for what is, not just what could be or what the last pole looked like.
That makes perfect sense. Then there's safety assurance. And this goes beyond just avoiding immediate structural collapse, right? Correctly identifying the framing type allows you to maybe predict potential fatigue points years down the line, especially where maybe an improper original identification might have created latent stress concentrations that only show up under extreme, maybe rare events. It's about preventing the invisible failures, too, ensuring the structure can withstand not just normal operation, but also maintenance loads and critically severe weather.
And next up, think about construction efficiency. Having these clear, systematic decision criteria for identification right there in the field, it enables crews to select the appropriate materials and methods quickly for routine maintenance or, crucially, emergency repair. It dramatically reduces the need for extensive on-site re-engineering, streamlines operations, and helps get power back on faster after an outage. That's huge.
Definitely. And underpinning all of this is system reliability. It seems obvious, but proper structural design informed by accurate identification at every single pole location is just foundational to overall system reliability. It's kind of the silent hero that prevents cascading failures during challenging conditions and significantly reduces long-term maintenance needs. Every pole, correctly identified and assessed, contributes to the grid's resilience.
Well said. Now, this diagnostic tree we've walked through, it's an incredibly powerful framework, it really is. But real-world scenarios, as we both know, are rarely textbook perfect. So what other considerations should an engineer or maybe a field supervisor keep in the back of their mind when identifying or assessing these poles? Factors that might explain why a pole looks the way it does, even if it seems to maybe defy the initial logic of the decision tree.
Exactly. That's a great point. Because what's truly fascinating is how experienced engineers layer additional context onto this framework. They understand that real-world applications often involve other considerations that really influence why a particular framing type was chosen originally, or maybe what its current condition implies now.
Absolutely. One crucial factor is simply environmental loading. In regions prone to severe wind or heavy ice, a structure might appear over-designed for what looks like a simple tangent application. But that additional robustness isn't waste. It's there for a critical reason: to withstand predictable extreme weather events. So you're kind of reading the pole's resilience to its local climate, too.
That's right. And another often overlooked aspect is future expansion. Sometimes maybe a pole was initially built with stronger framing than its current conductor load strictly requires. This isn't necessarily an error. It could be a strategic planning for anticipated system changes, like future load growth or maybe higher voltage upgrades down the line. It's about seeing beyond just the present configuration.
And we can't forget maintenance access. Just how crews will perform maintenance, or even the temporary loads from equipment like bucket trucks that might influence the structure's design sometimes. Then there are those terrain constraints we touched on with slack span. Site-specific challenges like rocky ground, steep slopes, or really tight easements can severely limit standard framing options. That forces ingenious solutions like slack span, or requires modifications you wouldn't typically expect to see.
Right. And finally, there are always standards and code compliance, utility-specific engineering standards, the National Electrical Safety Code, NESC, other regulatory requirements. These can mandate certain framing approaches regardless of the basic structural analysis. Sometimes a design choice isn't just about the pure physics of the load, but about strict adherence to established best practices and regulations that ensure safety and interoperability.
This really brings up an important point. While our decision tree is incredibly sound for identification, it's definitely not a substitute for seasoned engineering judgment. Not at all. It's an unparalleled starting point for rapid field identification. Fantastic for that. But it should always be combined with that deeper understanding of load analysis, local environmental considerations, and applicable utility standards to truly grasp why the pole looks the way it does, and what its full implications are. It's a powerful lens, maybe, but not the entire vision.
Well put. So ultimately, this approach, it transforms what could be a dizzyingly complex engineering assessment into a more manageable, actionable process for identification right there in the field. It helps you ensure that each structure you encounter provides that crucial balance of strength, economy, and reliability.
Yeah.
That ability to read a pole quickly and accurately, it truly is a kind of superpower for any electric utility engineer.
I agree. And this deep dive into identifying pole framing types is absolutely essential, I think, for anyone involved in overhead distributions, system design, or maintenance. And it builds nicely on what we discussed Monday with heavy angle framing and Tuesday with vertical framing, setting the stage for the next couple of days.
Exactly. And looking ahead in our PXRD newsletter series for the rest of the week, tomorrow, Thursday, we'll be taking a deeper dive into tangent framing specifically. We'll explore its nuances, even though it's common. Then on Friday, we'll wrap up the week with an in-depth look at deadened construction, bringing everything full circle and really solidifying those critical tension management concepts.
We truly hope this deep dive today helps you feel even more confident and insightful the next time you're out fielding a pole. After going through this today, what specific aspect or maybe visual cue stands out to you most about how you'll approach identifying these framing types now? Something to think about.
Definitely. And if you'd like to leave any feedback on this deep dive or maybe have some questions, please feel free to reach out to me. I'm at alex.reed.power.podcast@gmail.com.
Or you can connect with me at emma.quinn.power.podcast@gmail.com. Thanks so much for joining us for this deep dive. We look forward to connecting with you again soon.